Very good. So let's jump to a little bit more of the details. We looked at global circulation, global winds, and so on. So let's begin to zoom in to smaller features. One of the things we want to learn is the difference between weather and climate. And I can show you in a minute here that you actually can be a simple climate forecaster. How? So today I'm recording this on what's the date today? September 8th, right? So it's very hot, not rainy. Should be raining still, monsoon, but on a given day it may not rain, right? Because monsoon doesn't mean it will rain every day. So what you can do is then think about uh, a day in December 8th, September 8th versus December 8th. What do you expect on December 8th compared to September 8th? September 8th, you know, is going to be either rainy or hot and humid like it is now. December 8th, you expect is a winter, even though it's a tropical country. You expect dry and cooler temperatures, unless you are in a place like Chennai where it could be raining because they get northeast monsoon, right? So you know what to expect in a given month on a given day or so, because that's climate. Over a long time, you expect that certain time of the year, certain day of the month, will have a certain type of weather by long-term expectations. But as I said, on a given day, like on September 8th today, there is no rain. This is weather. And on December 8th, it's possible that you will get a freaky rainstorm even in a place like Mumbai. Or it may be in Chennai and it's not raining, even though it is the rainy season, and so on. So climate is what you expect, weather is what you get on any given day. The other thing we will come back to later on is the concept of feedback. What does it mean? Even though sun comes up and sun goes down, so you have a warming of by the sun's radiation during the day and no heating at night, and even cooling because the infrared energy or the long wave is going out to space. But during the day, you can have weather change many times. It's sunny now, but in a couple of hours, in 2 hours, it could be raining. Why does this happen? Essentially because there are a lot of feedbacks in the system. As the Mumbai city warms, it begins to develop some atmospheric instabilities. It begins to demand moisture, or the winds just begin to change and they bring more moisture from the Arabian Sea, which is very warm these days, right? So the feedbacks make many more time scales than what the sun's forcing provides. Okay, so on a longer time scale, we talked about ocean providing the feedback by storing the energy and releasing the energy at much longer time scales than the seasons. So the intrinsic time scales of forcing are the diurnal cycle and the seasonal cycle. If you go on a very long time scale, of course, we said the orbital parameters like the ellipticity, the obliquity, and the precession also change. But on a generally human lifetime, we expect diurnal cycle, sun going up, sun going down, and the seasonal migration to be the forcings, the intrinsic time scales of forcing, unless you are beyond the polar circles, Arctic Circle and Antarctic Circle, in which case you would have 6 months of diffused sunlight and 6 months of darkness and so on. Okay, so given all that, what happens locally? You have things like cyclonic flow and anticyclonic flow. Here again, you use your simple Coriolis knowledge to do this. Let's say you have somehow created a high pressure center. We're not talking about the subtropical high. We will look at the cyclonic and anticyclonic flows around those kind of large pressure centers. But let's say this is a smaller scale, local high pressure system, which is bringing right now clear skies and sun into Mumbai, for example, right? So relatively speaking, there is a high pressure, because if there is a low pressure, soon you're going to have clouds and rain. So use your Coriolis. What kind of flow do you get around the high pressure? You expect that if there's a high pressure center, there is low pressure all around it, so air is going to flow out of the high pressure towards low pressure. Coriolis is going to try to turn it to the right in the northern hemisphere. So you can see this figure that flow is going from the middle to out, and the flow is getting turned to the right. So soon you have a clockwise flow around this high pressure center. The analogy used in the book is this tightening of the screw versus the loosening of the screw. So the cyclonic flow, on the other hand, like a cyclone or a typhoon or a hurricane, comes from having a low pressure center, right? So how does Coriolis work here? If there is a low pressure center, you have high pressure all around it, so flow is trying to come in, and you add Coriolis again, and you end up with this counterclockwise or anti-clockwise flow, right? The term cyclonic and cyclone come from Greek word which means going in the same direction as the Earth's rotation. So low pressure systems rotate counterclockwise, which is the direction of flow of the Earth around its axis in the northern hemisphere, because in the southern hemisphere cyclonic flow will go the other way. Okay, it's something to remember again. North, south, always opposite. So anticyclonic and cyclonic flows are those simple things. Land sea breezes are related to the differences in heat content. During the day, land warms faster, warmer temperatures, low pressure, ocean warms slower, so you have high pressure on the ocean, so wind will go from the ocean to land and give you sea breeze, whereas at night water cools slower, so ocean cools slower and tends to be warmer. And the heat content of the land is very low, so it cools really fast compared to the ocean, so it gets colder and high pressure, and the ocean is warmer and low pressure, so then the air will go from land to sea. We call it the land breeze, right? So these are the kind of processes that create various air masses. In a large continent like Africa or Europe or US, you will get multiple air masses occurring at the same time. They're also at a latitude where the polar jet stream that we talked about, and we will talk about some more, wobbles. You can think of the polar jet stream as a referee between the cold polar high pressure air versus the lighter subtropical tropical air, and so the air is pushing in one way, the pressure and cold air is pushing the other way, so the jet stream tends to wobble. So it can bring cold Arctic air in one place and push the warm subtropical air in another place. That's how you end up with these kind of wobbles. So let me stop this here and then introduce the concept of cold fronts and warm fronts in a minute. Fronts are essentially one air mass is ramming into another air mass, and the processes there are again very interesting. So we'll see that in a minute.